Okay. How was the exam? Reasonable? Okay.
Other than convincing myself away from the right answer in that one instance.
Yeah, so maybe I can comment on that. So I would say, third question, some of you got it right, that was good. But if you were not sure about the answer, one thing I would say is that typically what happens is that it's very easy for all of us to get mechanical about, like when we are taking derivative, you get very mechanical and, oh, give me a function, you follow a prescription, like that's very standard, the way coursework works. There is this very similar kind of questions that is always asked. And I would say in the third problem, right? It was the third problem, I think. Yeah, if you did not expect, if you did not know the answer right at the first step, even before you began, that means you're being too mechanical. I think that's the way to. I mean, it might be a harsh statement, but I think it's reasonable because in the very first line, you can see that it is actually 0. So even now, go back. If you're not sure what I'm talking about, go back and look at it. You should be able to write, oh, this is 0. I don't have to do anything. It should be the work. But otherwise, I mean, it's okay. Like it happens all the time that when you're learning, first you learn the procedure, and then you see the depth as you go more and more examples, you see the depth, you see, oh, I should have seen this. So it's okay if you're not seeing it. But that's my point. That
I think the frustrating thing is intuitively my initial thought was that should be 0.
but then you trusted your work more.
Then I convinced myself otherwise. Even if I followed my work and skipped, the one mistake that I made in that, it would have come out to 0 if I would have got it. But my brain was like, it can't be that easy.
Okay. I think again, this is like this becomes, I feel this becomes important in research also. Often people take this to extremes and discuss this at various levels. Like research is a point where you don't know the answer very well. You might be the first person doing it. You might be taking a very tedious path, even though it might be there might be a short way to it. You might be taking such a long and tedious path that you won't trust yourself. Oh, I must have made 10 mistakes. So you have to have a guiding principle that somewhere you should have a trust that no, this is it. And typically people say there is a geometry and algebra, like there is a, historically speaking, in mathematics, algebra came very recently in the last 500 years or so, where you really have coordinates and you could write down equations of a curve and all that. That's very recent, like by recent I mean 500 years. Before that, it was just thought, and you have to visualize the whole thing, and there was geometry playing a big role. And often people have a lot of strength in geometry, and if you can see things geometrically, then it might take a very long process to prove it. But both have to come hand in hand. But you have to have both. And this one, I would say, is that geometry part where you could have seen that right away, in a sense. Okay. So try to develop both. Again, I'm not saying it's easy. Don't feel bad if you couldn't do it. If you could do it, that's perfectly fine. Even that probably never always doesn't mean that you could do it, because maybe you did algebra first and then you realized it. Either way, but that's just recommended. If you call it preaching, this is a way of preaching. How to do research. It should not be done. Research should be done in your own style. Okay. Let's see. I have already curved the exam. It's not exam, like I curved the score. Is that familiar what I do? Maybe I should once mention it. Come on.
Definitely, you get you a camera that you can program that at once and then.
Yeah, that will be good. Sometimes I'm teaching in this room all the time, then it works. I just have to make sure that the camera is in the right place. But this time I'm recording here and in this auditorium 440. So there, every time I change the settings. I mean, I shouldn't be complaining. I should be coming earlier to this. So that's all. Not a good. So we have a homework board. This was a new. Hopefully to stop writing. Full, right?
It's almost like there's something on the board that's causing that.
Correct. It might be this because my room gets very warm. I put it on, put my heater on, and then I think this dries up. It could be this, and I'm hoping that after a while this start flowing. Oh, not. Okay. See one of these. I will show this. Yeah, I was saying about the curving of the exam. So that's midterm 2. I think it is in March, the end of March. Midterm 2 is end of March. I don't know the dates right away. Is this readable? Faster? Yeah. It's a little tough, but I think it can read. Maybe this will get better, but tell me there are more. I just try to figure out which one works. Bunch of them. Okay, I was telling that if your total grades, right, total is a homework plus exam. If your score was, let's say, in all this was about, let's say, let's make it 80. So what I've done is 80 plus 100 minus 80, and then I think I've given 10% probably. I don't remember how much it is. I think it is 10% I have given. 10% of whatever you have lost, and you have to also calculate your quiz grades. And it turns out that everyone has a 1 in this. Like, so whatever is your score out of quiz total, total quiz grade out of 1. Like I dropped one of the quizzes, so I think that makes all of you have a full score from what I can remember. So this doesn't really matter. So in this case, so this is 20. So 10% of that will be 2, right? So this makes it 82. If y is equal to 1. Okay, so that's what I do. I do this 4 times in a semester after midterm 1, no, 3 times after midterm 1, midterm 2. And then final exam. In this case, it is 10%. Sometimes when the exam is very hard, then this can go all the way. It has happened that I have made it 30% or sometimes even very rarely higher. earlier when I was teaching it for the first time, I think the course was a bit harder, I don't know, for various reasons. I teach it hard. So there were situations when it was 50%. I have given it. That's just for your information. Any questions on that? Especially, like you guys know. Okay. Okay. So let's proceed with what we were doing. We're trying to understand the pattern that was observed back right about within 100 years of Newton writing his Newton's equation, that there exists a action which is written in terms of a Lagrangian, which seems to be always giving the Newton's equations of motion. So, so we say there exists an action. Let's say this is part of a okay. So we say R. This is position as a function of time. So this is the path. Like given time t1 and t2, we are usually interested in some mass. Mass is typically the system. It could be a planet, or it could be a point particle. It could be an electron, or it could be a real point particle, or a system of particles. And the mass is the system m, and we are interested in the position of that mass, which is usually described by the center of mass. And going from T1 to T2, what is the curve, if you want? This curve satisfies the Newton's laws of motion, but we want to write it as there is an action which is dependent on this curve, right? So this action changes if you were to change the path, and that's equal to T1 to T2, let's say dt prime, and there exists a Lagrangian, which is a function of, last time when I did it, I think in one variable. This time the only difference is that I'm doing it for a vector. So this is a function of the position. It also depends on velocity. That's derivative of position. And it could explicitly depend on time. Let's say, oh, T prime, right? All this is T prime. T prime. This often we will say is velocity. I'll try not to write that explicitly, because this gives the indication that R is the, like if I have to make any change, I make a change in R, and correspondingly the velocity will also change, or the derivative will change, but R is the actual quantity that is changed. This is called the action. We already pointed that out. So this is called the action. That's the Lagrangian. It's also good to point out at this stage that these two time dependencies are implicit in a sense, implicit. And these two time dependence here are explicit. Here it's not going to play a significant role at this stage, but when we actually talk about very soon, within the, probably in the next lecture or so, we will talk about variation at the boundaries not being zero, and at that time we will have to differentiate between this implicit dependence and explicit dependence. We made this change here. We made the variation in here, and we said this is change in action with respect to a change in the path taken by the particle. as a function of time. At each time you make a variation, and this turned out to be equal to T1 to T2 dt prime, and this was equal to delta R. There is a time dependence in here. I'm not writing that. So dotted with EL by, that's your gradient, right? Gradient. The first, that's a variation due to this piece here. Plus, there is a variation in here also. So let me write that as d by dt, or better, let me write it on the right hand side. This also I can write on the right hand side. EL by, for convenience, I'm writing this as variation with velocity by dt of delta R. We write this also onto the left in case one wonders why I'm doing that. So the variations are on the right. So that's what we got. Next step you do is that you take the time, you integrate by parts on the other side. Don't worry about the boundary, and you would say this is equal to, let me write the next step, T1, T2, T prime minus of e by dt dotted with. If I require an extremum principle, stationary action principle. Oh, thank you. Yeah. So, principle of stationary action. So, a stationary action principle says that you should set this to 0. And you immediately learn that this is gradient of the Lagrangian is equal to time derivative based on the fact that if you were to compare this with your Newton's laws of motion, it seems like this is the change in energy, negative of the change in energy often that comes about. And this is probably the momentum. So you define at this stage what is called the canonical momentum. Canonical in the sense that if you take a very simple system, like for example, a mass falling under gravity, this will really be the momentum that we study in undergraduate physics. But in general, this need not be the standard mechanical momentum that we are familiar with. And we'll do the example that we started last time. We'll try to finish it. So P, canonical momentum is P is equal to 4. In that sense, your equations of motion is simply dp by dt is equal to the gradient of the Lagrangian. This is often called the Euler-Lagrange equations. And I haven't been very insistent on pointing this out that I'm like this is a position as a function of time, right? But that can be written in terms of rectangular coordinates or spherical coordinates, or for that matter, any coordinates you want. And when you have a general coordinate that you take care of, then it's called a generalized coordinate. If you, for example, if you have a 3-body system, then you'll have 3 coordinates for each of the masses. So in general, there will be 9 coordinates, and often it is convenient to choose these coordinates in such a way that some of them are constants of motion. And that's a big motivation for the whole kind of developments we are, or the kind of formalism we are building. But I'll stick to writing always R of t, even if there are n variables, I'll write a position for that. Like if there are n particles, there will be n position vectors. It is more intuitive the moment you take it to the generalized coordinates. There is a lot of strength in that formalism, but whatever we do here, it'll be convenient to just think of it as position vector, and that should be good enough. Okay, well, that's your momentum. But now, if you go back here, you notice that what if we were to interpret this as, notice there is a function here, L, dependent on position, and this is, I said, velocity. But remember, this velocity is not really independent, right? It is position that is leading. If you specify the position as a function of time, velocity is no. So it's not an independent quantity. And let's try to remember what's variation of such a function. Right? So let's recall. So if I have L as a function of R, it doesn't have to be a vector. Think of if just to, since we're first time doing this, if there is any conceptual issue, get rid of this vectors. I can make it one dimensional, R, V, and T, because all this goes through in one dimension also. Then you say that, okay, what's the variation in this? All possible variations. Think of this as a simple mathematical partial derivative. So you would say that d by dl, so dl by dt would be the 3 possibilities, right? There's an implicit dependence in here, and there's an explicit dependence in type. And you would say this is dr by dt dotted with l by dr plus dv by dt dv by, why did I get dv by dt? Are you getting it? No. No, this is okay. Yeah, this is okay because I'm not one. Yeah. So this is dl by dv plus dl by dt. That's not the way I want to write it, but this should be a familiar equation, right? This is how you probably see in a partial differentiation course. This is a total derivative. That's the partial derivative, right? These are the partial derivatives with the quantities, and total change in L in a quantity is given in this form. Here, let's write this as, I want to make, remember what has happened here, right? The variation was in R, and we are asking what is the change in L. The same thing we want to write it here. So a change in L is equal to, that could be a change coming from R. So that's your dl by dr dotted with R plus delta L over the partial derivative with respect to velocity of the variation in V. But whenever I say variation in V, I should think about what is the variation in V here, right? If I write delta V, it seems like that is delta of dr by dt. That's not what is happening. This is R that is changing, so it is d by dt of delta R. So we should recognize that and say that this is d by dt of delta R. Make a change in R, what is the change in L? So that is an here, which is very similar to what is that. Why did I write that? Just to make you realize that this is nothing but the partial derivative. You look for variations due to a small change in something. Here we are making a change in time and you get everything. Here you can actually add a partial derivative with L, but that's going to be a total derivative. And since at the boundaries we do not have it, that's not going to contribute. Which is what we will do the change today. Two lectures down from here, we will actually put in that term and we'll see what else changes. At this point, these are the only changes that's possible. Right? That's your change in the Lagrangian due to a change in the position with respect to time. Now, here is an interesting thing that happens. Let's and remember your canonical momentum, right? So that's your P. So this is what is called like Lagrange transformations. Transformation. And this probably was a homework, right? I think probably. So the idea is, let's construct the following quantity P dotted with V. Remember, V was d by dt of R. So actually, let me write that in that manner. That helps. So d by dt of R. So R is a new quantity and minus of L R comma d by dt of R comma there can be a time dependence, but this time dependence really is harmless because it can contribute only at the boundary the way we are doing it, and we are not really changing things at the boundary. So time dependence at this stage is really harmless. What is this quantity equal to? I haven't taught you this, but this is a check on your undergraduate classical mechanics. Can you recognize that quantity? This quantity? Hamiltonian, right? So this is what gives you the Hamiltonian. So let's define this to be H. And at this point, you can ask, oh, what does the Hamiltonian depend on, right? It seems like here we had R, and then there was this, in a sense, velocity, but this is velocity is not really independent, right? That is R, and once you change R, the derivative is already known. P is the change in the Lagrangian with respect to that velocity, and you're not even sure how that works with respect to R, right? It has become too much to the next order. So it's not very clear what P is here. But we would like to know what are the quantities this depends on. Like Lagrangian depends on just the position, right? This action here depends only on the position. If you give me the position, its derivative is known, and I do everything. But it's good to know, what does this depend on? Like, does this just depend on the position, or there is a velocity dependence or the speed dependence also? And that's where this power of Lagrange transformation comes in. So let's see. Let's make a variation in H, and let's say, and we make how much ever variations we can. So this is R, we know how to do because R is actually the position as a function of time. P, we really don't know how to make that variation, but we will say that that's an independent quantity. But then this might seems to suggest, so that's the usual confusion that comes is, this seems to suggest that this should have R. Let me write that down. So it seems to suggest that there should be R d by dt of R, and there should be a P in here, right? And if you want P also, that's the quantities it depends on. But we will show that actually no, that doesn't depend. And that's the idea of Lagrange transformation, that you you start with this structure R and two variables, and you do this transformation, and you will get one of them will go away. So that's what happens in thermodynamics. You always deal with two variables at a time. The third variable always goes away. So let's see how you do that. So let's make the variation in all the quantities. So delta H is equal to, make the variation in P. So let's see if P dotted with d by dt of R. But I can make the change in R also and not change P. So that's P dotted with d by dt delta R. Notice here, if you write velocity V here, then it is the variation in V. So this variation is due to the variation in R. So that's a good thing to recognize. And L can change in both these, right? We're not changing RT. So this is, let's say, delta R dotted with dL by dr and minus of dV if you want. But when I write dV, I'm going to write this as d by dt of delta R dotted with dL by dV. So that's basically delta V, but it is a variation in R is causing that. Any questions there? Should be just mathematical steps. Okay. Thank you. So, yeah. Okay. Notice these two terms, this and this here. What is that? What is the combination of this two together? What is that equal to? Anything a little? Can use this one.
Is it the total time derivative?
Oh, simpler than that. These two compare it with this.
Oh, yeah, 0.
0, right? These two exactly cancel out. And that's the crux of Lagrange transformation. If you construct this, take any function f of x, y, and if you build this, this will always cancel out. Right? So this cancels out. And that seems to suggest that I have a change in R. So let me write this first, right? Usually you write R position first. So this is minus delta R dotted with dL by dr plus delta P dotted with dr by dt. And in principle, I should have had a third. See, notice we were predicting there were three dependencies in here, right? R, P, and V. I could have written this as dV, dV meaning this, right? Delta d by dt of delta R times something, but that's 0. Right? If this term is 0, what does that mean? That means that this function does not depend on. Right? This automatically came out to be 0. If I have a function f of x, y, z, and the variation due to z is coming out to be 0, that means there is no dependence in that function. So that means you say this does not depend on. So Hamilton does not depend on the velocity. Velocity means derivative of position. It only depends on p by construction. Right? That's the way you have constructed it. Like it cannot depend on v. If there is, that means it is because you have written it in such a form. Yes.
Last term.
Oh, come from, where did it come from? That is this term. Let me write that better. d by dt of delta R, right? That's this term, but it is 0, right? So it is P, so it should be reading it as P minus dl by dv. Correct? If I use the equations of motion, Euler-Lagrange equations of motion, that is what the Lagrangian satisfies. So it is not any function that has to be the Lagrangian there, which has that momentum associated with it. If you have that, that's 0. So let me explicitly write that 0 there. If that's a 0 there. If it is 0, then I know that it does not depend on velocity. Right? So Hamiltonian, you cannot write velocity in it. Whenever you write, sometimes you will say Hamiltonian is kinetic energy plus potential energy. No, kinetic energy has velocity in it. So you have to convert the kinetic energy into potential. Otherwise, it's not the Hamiltonian. It is a Hamiltonian function in the sense that velocity is a function of that. You can call it an Hamiltonian function, but it's not a Hamiltonian in the sense it won't satisfy the equations of motion. When you have to satisfy the equations of motion, you vary it with position, you vary it with momentum. No velocity is there. So you cannot vary that. So that's important, that has to be. So if you don't have any position, so that's your delta H. Now let's go back, and so what does this mean, right? If it is a function of only H and R, so then H is equal to function of only R and P. And there is time also, but we are keeping time is innocent here. We'll bring it back later. So if I were to think of this as a variation statement itself, this will be delta R dotted with variation in H with respect to R. R and P are not independent. So that's delta H over delta R plus delta P dotted with the over delta P. And that's the simple chain rule if you want. If I make an H, I can change it with R, change it with P. Earlier we did it with velocity, right? But velocity was a contribution coming from the derivative of R itself. So that's what it should be. But I got H to be this using the Lagrangian. So that means these two are connected, right? Equate these two. Right? So whatever is the coefficient of R should be the variation in the H. So I get two equations, equate this, equate this. Right? So it seems to suggest that the change in the Hamiltonian with respect to position, put the negative sign here, that's equal to the change in the Lagrangian, or the gradient of the Hamiltonian is negative gradient of the Hamiltonian is the negative gradient of the Lagrangian. Hamiltonian is typically the energy, not always. Oh yeah, maybe can be a quiz at this stage, right? Is Hamiltonian the energy all the time? Okay, so the quiz question is Hamiltonian always equal to energy? The answer to that, I give it already, is no, it is not. Then the second part of the question is, show me a system or give an example of a system where Hamiltonian is not the energy of the system. Energy of the system, like I think that is important. Or figure out what is the depth in the question as to what is the connection between energy and Hamiltonian. Okay, so that's one equation. So I was trying to make the statement here that if Hamiltonian is the energy, then negative change in energy with respect to, or negative gradient of energy, what is that equal to typically? Negative change in energy. Force, right? That's how we interpret the change in force is the man or system trying to reduce its and minimize its energy is what is manifested as a force. So that is the same as this statement here, right? If I use my Euler-Lagrange equation, this becomes momentum, derivative of momentum with time. But do that, or if you want, you can write this in the next step. Okay? That's dp by dt. Canonical momentum, if you want, but that's not a statement right here. So this is coming from when you equate these two, you just get that. Here you get dh by dp is equal to dr by dt. But anyway, we can use this because we have already used the idea of canonical momentum here in getting that zero. So as well use Euler-Lagrange equation and get to the next step. And these two equations are what is called the Hamiltonian equations of motion. So yeah, or maybe first step I should, I guess. Newton's laws of motion, right? So this is Newton's laws of motion. It says that d by dt, let me not write momentum, instead let me say mv, right? Or dr by dt. That's what it is, right? Second derivative, mass times acceleration, is equal to if it is a conservative force, this comes out to be negative gradient of am I correct something? So let's say, I think we wrote u. So that's potential energy. That's Newton's laws of motion. Next, we said what is Euler-Lagrange equation of motion. Equations, again, of motion. There you say that first you need the Lagrangian, and you have d by dt L by dv equal oh. And these two are identical. Right? This, you can start from here and get here, or you can start from here and get there. This leads to the idea that we can define, so this is a definition that Lagrangian with respect to. And next is we call Hamiltonian equations of motion. So, is this visible to you? Sorry. This is really good, guys. Try one more. Hamiltonian equations of motion, unlike Euler-Lagrange, is not second order, it's first order equations, and these are dr by dt. So this is basically the definition of velocity, if you want, right? So this is velocity, but let me not write v. Typically, it's not written like this. It's just dr by dt. That's, we have defined that to be the velocity. So you can write it, but I'll erase it for my own purpose. Okay, so this is partial derivative of the Hamiltonian, dr by dt, this will be dt. And e by dt, remember r and p are independent in the Hamiltonian. It's not like the earlier case when r and v were dependent on each other. Right? So velocity was just the derivative. So this is negative gradient of the Hamiltonian with respect to position. Okay. And Hamiltonian plays a lot more stronger part in physics, primarily because we do not know how to do quantum mechanics using Lagrangian. We only know how to do quantum mechanics using the Hamiltonian. Like it is a Hamiltonian you begin with, and you write down your commutation relations and so on. So it plays an important role the way it is constructed that. And I've tried to motivate this to a certain extent. As we are proceeding in this formalism, we will reach what is called the Poisson brackets. Right? We will reach Poisson brackets, and that is where you will make a connection with quantum mechanics. So we will do that stuff, but that's not necessarily a proof or anything, but that's a strong indication that, oh, this is how one should make the leap into quantum mechanics. Okay, but having said that, so that's what you will need for your homework. In your homework, there are about 2 or 3 problems where I tell you, I think the problem says you start with this, right? You have to actually get the Euler-Lagrange equation, and then there is this Hamiltonian equations which is involved in here. So, and if you are interested, you can proceed and try to solve the equations. So take a simple system, write your Hamiltonian equations of motion and do it. It's very clear what happens if it is a simple system. This is P is mv, right? That's your velocity. You just have to substitute that in there. And in simple systems, it's very straightforward. But the best system to deal with this is magnetism. So if you take a magnetic field and put in there, it turns out it is non-trivial. That's what we will do when we are doing Poisson bracket. So it will turn out that velocity and or the meaning of velocity changes, right, in magnetic field. Right? It is no more mv. Like momentum is not just the mechanical momentum mv. That is a magnetic potential. And we will talk about that later. We were doing an example last time, which we did not really finish. So let's do that in this context. And so that's is, and you have to do the relativistic version of that, right? So we were doing an example where so we were doing an example of a charge in an electric and magnetic field. So Newton's, if you were to use Newton's equations of motions for a charge in an electric and magnetic field, not necessarily in a uniform, it's not uniform. So it's mass times velocity, that's equal to charge times the electric field, which can depend on position and time, and plus Q times V, V being dr by dt. That's the same. Crossed with magnetic field, E of E. Sorry. We said electric field is negative gradient of a scalar potential. And we said the scalar potential depends only on R and T, not on potential. And the same thing with the vector potential. It doesn't depend on velocity, d by dt of A bar comma T. And the magnetic field set is del cross or the curl of the vector potential. We substituted this in here, right? That's what we did last time. And I will not go through the steps again. So put these things in here and rearrange. Substitute this in here and rearrange. Refer to your notes from last time, from last lecture, which was about a week before, right? Because it was the exam, so you may not remember it, but still, I think, yeah, let's not go through it again because then I may not be able to complete this problem even today. So let's proceed. forward, and I have, and this leads to e by dt of mv plus q times the potential, and it's necessary that I highlight that it is not a velocity dependent quantity. That is mass times velocity plus a position dependent quantity is equal to negative gradient. Notice, if you compare this with, if you want a Newtonian, Newton's law, so that is d by dt of something is equal to negative gradient of, this should be the potential energy, right? So that's R and T minus of Q times V divided with A. I probably might have highlighted last time, what's the relevance of this negative sign? Might have highlighted, I don't remember. Or what is this? Q times phi. What can you connect with it if you have to think of physically what is happening? What does that mean? That's an potential energy of a charge interacting in the presence of other charges. Let's say there is charge Q, and there is Q1, Q2, Q3. Right? So this creates a potential phi here, and that's the interaction energy between Q and all these charges, electrostatically speaking. Right? This is Q1, Q2 over R, Q times Q1 over R, Q times Q2 over R. This could be at different distances. That's what that electrostatic energy would mean. What is this?
Magnetic potential energy between currents.
Correct, or currents, exactly. Because there is a velocity, each of this charge moves with a velocity, right? So this is having a velocity, that's having a velocity, that's having a velocity. So that the moment it has a velocity, it should be thought of as a current, right? So this current interacts with this current interacts with this current, that's magnetostatics, right? But it comes out with a negative sign. Like negative sign means repulsion and attraction are switched. If you were to do simple attraction repulsion, so whatever is attraction here will be repulsion here. And if you remember in magnetostatics, it is like charges in electrostatics repel, right? Positive and positive charge repel. But when it comes to currents, like currents attract, right? Like currents attract. So that's that negative sign. It's a crucial thing, except for the fact that this is not pure magnetism, remember. This is magnetostatics. There is a magnetism hidden here. Right? So if you're doing pure electrostatics, magnetostatics in the sense steady currents, even though it is moving, that doesn't mean that it is actually not statics as far as del dotted with J, right? So magnetostatics has this definition that it should be not generating current. As far as it is steady, that's perfectly fine. Magnetostatics doesn't mean that you cannot move. You can steadily move. If you're going with constant velocity, that's good. As far as you don't suddenly disappear, right? If the charge doesn't disappear, if you're constantly doing that, it's okay. As far as G is constant, that's perfectly fine. So remember that that's not pure magnetism. That is a little bit onto the other side. This should be, like usually the confusion here is that, okay, this energy comes out with an opposite sign, correct? But then you go and think about field, that is a this is the total energy in electrodynamics, which is equal to epsilon naught E squared plus 1/2 mu naught B squared, right? That's a positive quantity. Like always positive, square of two quantities. And this is one is positive, one is negative. And how do you reconcile your thoughts with that? And then the idea is that, oh, that's not the total energy, there is something in here also. So one has to be careful. And if you like, one can do examples that you can show that, oh, this shows up the negative sign, but overall, when you do this, this does come out to be positive. So one should be careful in. But we were okay. So we start with the Newton's law. We got here. And then immediately we can read it out, right? Read out your Euler-Lagrange equation. That means that dL by dV is equal to mv plus q times A. And one can also say that the Lagrangian, so dL by dR is equal to minus or d by dr of minus q phi plus q times b with A. This immediately implies that this can be a possible solution is L is half mv squared. Because if I differentiate the velocity, I get mv. And this doesn't have any velocity. So the only thing that can give is that a linear term. So this is a constant as far as velocity goes. So it is q times v dotted with A. Right? And I can always have a constant as far as it has no velocity, it's okay. It is position and time is possible. Plus some constant. Same thing in here. This is now, if these two are correct, that the Lagrangian is the inside bracket, whatever is in the parenthesis. So this is minus q times phi plus q times v dotted with A. And there could be a constant, another constant, C2, that depends on velocity and p. It seems reasonable, at least one solution, not necessarily the solution. And in your homework, again, you see that the Lagrangian is anyway not unique. So what's the big deal? You just need one Lagrangian. So put this to be the mv squared, this to be your q phi, and you learn that the Lagrangian is equal to half mv squared and minus q phi plus q times v dotted with A. Again, this has this challenge. See, when you think of it in this manner, it seems to suggest that this is the energy, right? This is your interaction energy. But we already saw that that's not the complete story. This is the interaction energy, but that's not the complete story. That is an A in there. One should be careful about it. So this is a little misleading when you say that this is kinetic energy and that's your potential energy. It is correct statement, but it is misleading because this velocity has this A dependence in there. It's a mechanical velocity, but the canonical momentum is missing. In that sense, it's good to go to Hamiltonian. So let's talk about the Hamiltonian, right? How do you construct the Hamiltonian here? Go P, right? So let's define our P. Right? The canonical momentum is dL with respect to velocity. That's equal to mv plus q times A, which you could have seen right there, right? That's your mv plus qa. That's your canonical momentum. Notice P is not mv. This is canonical momentum. This often is called the mechanical momentum. So if you have that, let's proceed and find the Hamiltonian. Hamiltonian is P has to be dependent on, Hamiltonian always has to be written in terms of P and R. That cannot be any velocity, but momentarily, let's write that as velocity. E dotted with V minus the Lagrangian. That's P dotted with V minus half mv square plus q5 minus qv divided with A. That's good. This is the Hamiltonian in a sense, but this is wrong. This is not really the Hamiltonian because this does not satisfy equations of motion. You cannot take the derivative of h with respect to position and momentum and get your equations of motion. For that, first you have to get rid of v. You have to replace all the v's, only r and p's. Remember, h has to be written in terms of r and p. So even though this is the Hamiltonian, it's not really because that is velocity. So replace your all the velocities you have to get rid of using this equation, right? So what you do is, okay, come down. So P dotted with V is P minus EA over M plus minus of 1 over 2M. So this is P minus EA square. Right, and again, one more plus Q5 and actually it is usually, even though this is the long way I'm doing, do this first, convert this all into velocity, one piece of velocity, and then do that. It would be slightly simpler just because I'm short of time. I can see that more clearly. So this is P dotted with V. Or first replace the, I was saying, first replace P with V, right? Which is wrong. It seems to be in the wrong direction, but that will turn out to be slightly simple. So this is minus of mv square plus q5 minus qv dotted with a. Notice that qv dotted with a cancels out, and you get half mv squared plus q times 5. And this is the most confusing part if you want, it could be confusing. Remember, I have written the Hamiltonian as half mv squared plus potential energy, right? That's kinetic energy. That's potential energy. Agree? But what's wrong? There is no magnetism. Right? There is no magnetism. That's electrostatics. That's kinetic energy. That's the misleading part of writing the Hamiltonian in terms of velocity. That's not the Hamiltonian is not written in terms of velocity. So that's not the way to write it. You have to replace that. So you write it as p squared over 2m. So then you say, oh, 1 over 2m. And then you see the magnetism coming in, P minus EA squared plus Q5. This will satisfy your equation of motion for the Hamiltonian. Okay. Is that clear? So this is misleading, right? So you can ask the question, where is magnetism? That should clarify that what's the challenge with having Hamiltonian in terms of velocity. Okay, I have 5 more minutes. Let me try to see how far I can go with the Hamiltonian equations of motion. Hamiltonian equations of motion is dr by dt, basically the definition of velocity, if you want. That is equal to dh by dt. P appears only at one place, so it is 1 over m P minus EA. That's it, and that's indeed the definition of velocity, right? So this is mv is equal to P minus EA. So that was the same statement as our canonical momentum. So we have like eventually everything is the same. Right? If you are working with Hamiltonian, you will begin from here and you will write your equations of motion, and you learn that this is the case. This is how you would have learned that in the Lagrangian scenario. You learn it here using the first equation. The second equation is the rate of change of momentum. That's equal to negative gradient of the Hamiltonian with respect to the position. Remember, position is there in A. So there was A of RT, right? And there is phi also. So change. So this will be equal to 1 over 2m. So I have to write gradient of this, correct? So this is gradient. So this is 1 over 2m. Yeah, for a moment, if you allow me, so V is that short form of that, right? So if you allow me, that's 1 over 2m. So it is gradient minus, right, of velocity dotted with velocity m. So it's, I put a m, p minus v is mv. So it's v, p minus is m, so it's half m, right, m on the top. V dot with v. With the understanding that v is a short form for this. Right, so that's what it is. Minus of q times gradient of phi. Right, that's your electric field you want, but not yet, right? Because there could be a by dt also. So it's not the total story again. So we are convert this back. So put this all together. I can hit v, right? So it is v. How do I do this? Gradient of v dotted with v. So let me say this as, so it is minus m. So there are two v's, but both of them are identical. So this gradient of v dotted with v. Right, one v in that form, the second v in this form, if you want, and then we will have, can I get some help? Let's see. Now let's bring this from here to there. So there's this dp by dt. 2 minutes. So we have time derivative of p, which is mv minus mv minus ea. That's equal to gradient minus of dotted with v and dotted with mv. Mv is nothing but p dotted with a. Oh, maybe I should highlight one point here, that what am I trying here? If I am interested in the Hamiltonian equations of motion, I should stop here in principle, right? This is just p dotted with e square, and I can stop here and that's it. Right? But here what I'm trying to do is that I'm connecting it back with this. And I'm saying that, oh, this is nothing but these two equations are nothing but these equations again. Right? So whether we do Newton's laws or Lagrangian or Hamiltonian, all of them should be the same. So I'm trying to go undo this whole thing and go back and start whatever we started 1 week back. So that's what I'm trying to do here. So that's your total derivative, but there is a position and time dependence here. So this is d by dt of mass times velocity. That's what you would do in Newton's laws. Bring this to the right. Oh, that is minus q. I didn't write that, right? Minus q. Sorry. Minus q gradient. phi. So that's equal to minus V with P minus dA and minus Q gradient of phi plus E times, so that's a total derivative. So I do E is Q, so I replace that. So it's Q times partial derivative of A with respect to time. And I have plus Q times velocity. So that's dr by dt, which is nothing but velocity dotted with a gradient of A. These two clearly give you your, what happened to my sign? Something went wrong. Gradient of phi and minus derivative of p. This should be negative. So bring us to the left. So mv minus, oh, mv plus e, right? But yeah, I was replacing p, so it is mv plus e, right? This was p, so I replaced, so that's plus e. I changed that, so this makes it minus here, and this makes it minus there. Okay, so I have got one piece here, that's your electric field. So that's minus q times the electric field. And here we can write this as, let's see, so that's negative gradient of V dotted with V. And this is negative gradient QV dotted with gradient of A. Substitute this again. But this is okay. How about we'll do this next time? So homework, right? In your homework, you're sure that this is actually, this leads to QV cross B. That has to be this. Sorry, this is plus. This is plus because negative gradient. And this is QV cross B. V cross del cross A. So try to back calculate to expand this and probably should come out that. But I'll stop here because you guys I know have some plus, so but you will need this in your homework. Like, and remember in your homework you're doing the relativistic questions. It's a little more messy. So make sure you first do this and follow the same thing. In homework, what changes is that all this will remain the same. It is a kinetic energy that changes. Kinetic energy in relativity is not half mv squared. It has a denominator also. So that's the tricky part. So all these parts will remain the same. It is a kinetic energy that will come. So hopefully you guys will manage. Otherwise, take help from me. Sorry, kept you hanging. Right.